Hello, Ray. It's good to see you again.
Yeah, you too, Richard.
We've continued to get good responses and good numbers on our science slides and conversations. I'm very pleased.
Yeah, it's good. Still a lot of people asking, when are we going to tell them what the share market's going to do?
I think we put out enough financial content that, we don't have to focus on that here. So there's plenty of other financial content that we're putting out. Appreciate that, the rubber meets the road in markets, so to speak. But I'm really enjoying this, and I know other people are too.
Yeah, that's great. Yeah.
So you shared with me that there was some news out this week that was relevant to the last conversation that we had.
Yeah.
Would you like to talk about that a little bit?
Yes, for sure.
Okay, let me just bring it up on the screen here. So let me get my screen share here. And I believe that this was it, NanoGrav. So NanoGrav is a research group, or is it a government entity, or?
Well, I think it's a collaboration, really, from a lot of different ones. There's 3 different radio telescopes involved and lots of astronomers from around the world. They've been doing this for 15 years now, and they've been putting things out every few years saying what's the status. And for the first time this time, they're saying there's now enough data and it's clear enough that they can get a good picture of what's going on, and they're calling it the gravitational wave background. So they can detect waves of different lengths and different periods that are showing. So the way they do this is they're looking at what they call millisecond pulsars. So a pulsar is the remains of a star that's collapsed right down to very small. And as a result, conservation of angular momentum, it rotates extremely fast. And these are the really super fast ones that rotate about 1,000 times a second. They might be, some less than 1,000 and more than 1,000, but they're in that range. That very fast rotation, and they're very, very regular. So of all the things we know outside of some of the atomic oscillations we use for clocks, these are the most precise timing things around. And because they've got a bunch of them, I think it's about 65, they can get the timing from them, and they spread around the sky. So when they are looking at all of these with these radio telescopes and recording the timing of their pulses, they can combine all that together, and they can find out which directions in the sky are they taking slightly longer and slightly less time at different times, because this is one of the effects of gravitational waves. It makes space expand and contract a little bit, movements in the space. Now, this is closely related to what we were talking about, these I call them giant electromagnetic waves. Now, a long time ago, I used to call them giant electromagnetic or gravitational waves, because both of those travel at the speed of light. And we know that whatever this is travels at the speed of light, because those big wave structures we had the time periods and the distances matching on a basis of the speed of light. So it's really opportune that this comes up at this exact moment. So I said electromagnetic waves last time. We should include in there or gravitational. There was a reason why I stopped saying gravitational, and that is that ultimately I think I can show, and we'll perhaps get to this later, that gravitational waves are an effect of electromagnetic waves. And funnily enough, it's at the atomic scale where this happens, that when the smallest waves that we know about are the ones that make up the atomic particles. And they oscillate incredibly fast, like up to a million times per second. And these oscillations, in my view, if there's shells of stuff moving in opposite directions as you go outwards from them. And so that's called the wave structure of matter. it's consistent with a lot of the stuff that physicists come out with, but most of them don't think of it that exact way. But Milo Wolf did very good work on that, and we should cover all of that at some point. But once you actually start to understand that, when you get near a very massive object, then this movement of the space sideways slows down the advancing of light in the direction towards the object or coming out from the object. And this is what black holes are where the movement sideways is so big that the light can't make any advance towards the thing. And that's they used to say that no light can get out of a black hole, but in actual fact, I think they're now realizing that light can't get into a black hole either. It's a strange situation.
So let me just go back to these this new research here.
Yeah.
So make sure I understand it. So what you're saying, or what they're saying, is they're using these pulsars, which are celestial objects. I guess they're very dense stars. You're
very dense collapsed stars. After it's run its life.
Did you say 1,000,000 times a second?
No, 1,000. About 1,000
times a second. One full rotation, 1,000 times a second. And so they're able to use these essentially as clocks.
Exactly.
And then measure gravitational waves.
Yeah, because gravitational waves... What they call
gravitational waves.
Yeah. When we observe some of Einstein's early predictions, where when, for example, a planet goes behind the sun, there's a slight change in the time that the light takes to reach us when it comes near the sun. And that's because of the strong gravitation of the sun. And those things have been confirmed that it does exactly what Einstein said it would do. So it's understood very well. Einstein's formulas have all worked correctly. People keep thinking there might have to be some adjustment to them under some conditions. At this stage, that's never been demonstrated as being needed. They do work. So, yeah.
And so did the structures that they found in the gravitational waves align with some of your harmonics theory?
At this stage, I don't have any periods that they found in them. They've got a graph that sort of shows it from the longest to the shortest of the background, which is sort of like that black part in my diagram of between the waves. So I want to get some of their data. Unfortunately, with these papers, they have like about 100 names on the things that contributed to it. So it's a matter of finding the right one to send an email to and say, can you please send me some of this data to look at? And so at that point, it should be possible. I don't know, the data may or may not allow the determination of specific periods in it. I suspect that there will be some of the longer periods. So they've been doing this for 15 years. So it may show some of the things between sort of a week and say 40 months. For example, there might be those waves in there. The longer ones, we won't have enough cycles to get them. But I think it'll be possible to pick up some of those, but it may not be.
Okay.
We'll give it a try.
All right, we'll look forward to hearing from you once you get the data.
Yeah.
Very good. Well, thank you.
So that was very opportune that came at that time when I'd just been saying, here's proof that these waves, huge waves, exist in space, and they come out and say, yeah, they got them too.
Right. And speaking of science and scientists, you wanted to share a quote from Irwin Schrodinger. So tell us a little bit about who Schrodinger is and why you want to share this. Well,
Schrodinger was one of the main ones involved in the quantum mechanics when they gradually unraveled that. And his equation is, Schrodinger's equation is the sort of most fundamental one that came out during that time. So he's right at the center of things. It's a funny situation. I think we should mention, because someone else will if I don't, that he did that work while he took off with his girlfriend, his mistress, and did all the work, went on a dirty weekend, and did that, plus solved this equation as well. But he's also known for having had a fancy for teenage girls. So there's some bad things about him, but his physics was incredibly good. And so I think this one it's not quite in our category with Dewey and Krzyzewski, but it's extremely important in terms of physics. What we observe as material bodies and forces are nothing but shapes and variations in the structure of space. Particles are just, so here's a German word, Schaumkommen, I may not pronounce that right, appearances. So he's saying there is just this whole field of waves fluctuating about. There's no discrete objects in it, that they don't exist. It's just all this space bobbling about. And there's other people that I'm connected with that call things the wave structure of matter. They have that same view that that's how things happen. And I'm sure some other physicists have probably understood this, but a lot of them, particularly de Broglie, but a lot of them don't think that way. They think there are particles, and they have this wave-particle duality. It's not really true. It's just waves. So I think that one's important for understanding the universe.
Where do you think the wave-particle duality comes from? Why are people confused about this?
Because when they measure, for example, when they do the experiments with putting light through two slits, for a wave will will combine and make this interference pattern.
Right.
And that happens. Then they started saying, well, what happens if we study which slit it goes through? Because they thought it's a particle. They're shooting electrons at it, or they're shooting light quanta. But when they do that, they don't get that pattern that breaks it. And that's because they're interfering with it, And it's they don't understand their own experiments. In Einstein was one of the main ones that showed that there are quanta of light, and that's where quantum mechanics comes from, that they can show that if you've got a tiny little object and some light hits it, it absorbs a discrete amount that depends on the wavelength of the light. And Planck made a law about that, which is the energy is equal to Planck's constant times the frequency that gets absorbed. The higher frequency has more energy in it. And because light is absorbed in that amount and released in that amount, they decided light is traveling in that amount. And someone as clever as Feinberg actually said light travels as photons, but he's wrong. It doesn't. There's the electromagnetic field, and there are physicists around who understand this today, but most of them don't. And so what happens is light is emitted as a discrete amount of energy from an atom, because the atom changes from one vibration mode to another, and that energy difference is released. But that then travels out as a wave all over the place, and it arrives somewhere else, and some of it gets absorbed in a discrete amount, but it's not traveling as a discrete amount. So they think there's a particle in between, but there isn't. It's just discrete amounts that get emitted and absorbed. So that revolution in physics hasn't quite taken hold. I would say I've come across a number of people who've clearly understood that in physics, but they don't waste their time trying to convince everyone else. And they understand a lot of the nonsense that's put in popular stuff on physics. There's a load of nonsense, but they can't be bothered with trying to work that out. They're trying to work out the next step. So that's important, yeah.
I mean, it does seem that there's been a historical quest to reduce the universe to atoms, right, and particles, and that there's something about that that metaphysics, I guess, if you will, that's very attractive to us in the West, because we can then like control everything, right, and supposedly recreate everything. So it's just interesting how obsessed we are with particles.
Yeah, there are particles, but they are waves. And this is why they have the uncertainty principle. If you've got a wave there, and it's all, around a center, then there is a location, which is the center of the wave, but it's not exact because there's all this going on. And it turns out that the uncertainty principle, it comes in about 3 different forms. The uncertainty principle is actually saying when you have some wave, if you want to work out its wavelength, it's related to the length of data you've got on it. The more data you've got, the more accurately you can get the period of that wave. That's what the uncertainty principle says. When I worked that out, when I first understood it, put it in a physics group, this is just saying this, isn't it? And they said, yeah, didn't you know that? so some of the physicists definitely understand that.
Yeah.
It's nothing mysterious, you know. It's just the more data you get, the more accurate you can get the period. That's all it says. The
Which
uncertainty
is
principle.
very interesting in and of itself. Yeah.
Yeah.
That it's our own data that's generating the outcome.
Yeah.
And the perception.
Yeah. By the way, with the CAT software, we can get about 10 times as accurate as the uncertainty principle. There's a limit to how accurate you can get, and on average, it's about 10 times as accurate. But they only say you can't get better than this, but you can get a little bit better. Yeah.
Very good. All right. Well, let's get into the next set of slides. And from what I understand, last time we talked, we were looking at large-scale harmonic structure in the universe. And now we're going to kind of move down the scale and look for harmonic structure in smaller scales. Yes,
that's right. Yeah. So first of all, in part, I want to get to the human scale, but first of all, we want to go to the scale of moons. And it turns out that we can find, just like I did with the stars, if we look at the distances of moons from their planets, it turns out that there are three at very nearly the same distance, and another three at nearly double that distance. Our moon is one of those, and it's at the double distance. So there are three of the moons in the solar system, the bigger ones, or quite big ones, that are at 0.00124 astronomical units from their planet, and three at 0.00248.
So those units aren't on this slide, Ray. Are these in some other units?
No, we'll come to this one soon. So that's okay. Yeah, I'm sorry, I haven't made a slide for that.
Okay.
And so that, and they correspond to periods of oscillation of 0.62 and 1.24 seconds. You'll hear people say that light to the moon is 1.25 seconds. That's right, it is. And so those two periods, there are some cycles we know in the seconds range and around there, but none of them fit those closely. So that's yet to be discovered. So, but it doesn't matter. We've demonstrated on all the larger ones that they are standing waves. So we're I think prepared to accept it applies to the moons as well. So I just want to mention that one in passing and going down further. This one is actually taking all the moons of the planets as they were some time ago. They keep discovering more. These space probes are they've got hundreds and hundreds of moons in the solar system now. This one isn't the whole that was done a while ago, but it won't have changed substantially. And this is periods in days running from there. Now you'll notice 14 days and 28 days, double. Triple that, you get to 84. Triple that, you get 250 odd.
So are these rotations around their planets?
The revolution period around the planets.
Okay, revolution period around their planet.
Yeah, so
and this is throughout the Milky Way, or
no, just in our solar system.
How many moons are there in our solar system?
Well, Jupiter and Saturn have got hundreds each now.
They do?
And
wow. Okay.
Mercury and Venus have got none. We've got one. Mars has got two, and then the other ones have got huge heaps.
Okay.
Yeah. So now the interesting thing about these periods and days are in the electromagnetic field of the Earth. There are a series of oscillations which are due to the sun, probably primarily, at 3.5 days, 7 days, 14 days, 28 days. Those periods occur there as well. This seems to be saying that the periods that occur in the electromagnetic field of the Earth are also occurring in the motions of these moons. So it looks like, and there's clearly a harmonic structure there: the double, the triple, the triple, the triple. And there's, I think, is it the next graph? Let's have a look. So we did this one once before. And down the left are all the expected order of the prime ratios occurring in the periods. And then in the middle there, I've gone from 586 million years down to some fractions of a year. and we'll see like 11.86 years was Jupiter's period there. And those matched reasonably well. And those periods in days down the bottom there in red, 154.7 days down to 6.447, those things are all observed in quite a lot of stuff. But there's another set, which we just did there now, 14 days, 28 days, 84 and 254 days. Those periods also were showing in that last graph. Now, that happens if you go, yes.
14, 28, 49, 84.
Yeah, not the 49, not the 49 or the 701,
14,
but the other ones are all there.
84, and 254.
Yeah.
Pretty close.
Yeah. Now, those ones, so back to the other one again. If you look at the left-hand side, sometime after that 3, 5, 7, and 3 there should be a 17 ratio. And if we divide Jupiter's period, which I've always said is a sort of a clock, it's 11.86 years. I've converted it to days, 4332.6, divide by 17, then we've got some ratios of 2s and 3s as we normally get for those other ones. So it seems that that 17 ratio is coming in there to get all those other periods. Originally, I didn't think the 17 and 19 would come in until the atomic scale, and they do appear again at the atomic scale, 17, 19, and 23. But that's sort of interesting what's going on there. So that's that's an odd little group there that occur in two things: the moons of the planets of our solar system, and the electromagnetism of the Earth have some of those same periods in them. What do we got next?
Okay.
So that's so we did those. So we did these. We've done the galaxies, the stars, the planets, the moons.
Right.
The next two things, there's no obvious things. Later on, we'll get to cells, atoms, nucleons, and beyond that, quarks or quarks, whatever we want to call them. These two scales in there are around about a mile and around about 2 inches.
So from moons to cells.
Yeah, but one's between those here.
Okay.
Or we can call them 1.7 kilometers and 5 centimeters.
Okay.
So those things should be concentrations. But someone asked in the questions to the previous videos, why have we got this? What do they call it? Bathtub. And this was the part where we didn't have the things. The bathtub, it was up at the ends and down in the middle.
Mm-hmm.
So
is that on this chart here?
That's correct. Yeah. So that was the bathtub that they were describing as a bathtub, which is quite a nice description of it, I think.
Mm-hmm.
Those X and Y, it may be that if we were at a different scale or at something, we would see them. But because we're so close, we don't just see X and Y, we see all the ones in between them as well. And that may be the reason. I don't know. I'm only guessing. Okay, so carry on.
Basically, we're not able to really find the same clarity of harmonic structures.
Yeah, we can find it.
Of 5 centimeters to a mile.
Yeah, we do. We find them. There's loads of them. But what we don't find is that there's particularly one objects that, like with stars, it's clear what stars are, what galaxies are, what planets are, and what moons are. But with these, it's not clear. And again, with cells and atoms and stuff, it's clear what they are.
So the categories.
Here, we've just got the whole spectrum of things there, and the harmonic structure's present.
But they don't fall into categories neatly.
They don't. No, neatly. No, they don't.
Okay. Yeah. All right.
That's just another version of the same thing. That was about the earliest one I did when I did those things. And
so again, X and Y.
Yeah, again,
between 6 centimeters and 2 kilometers.
Yeah.
Don't have the same, don't fall into the same categories. It's like the resolution is too high for us because we're so close to it.
That's my guess, yeah.
Okay.
It may be there's a real reason for it. Okay, now this is some rocks. North of where I live, a little bit away, there's a place called Red Beach. And there's a huge cliff there, which has got lots of nice geological layers. You can see it all the way down. And then the sea has worn it away. And at the base, there's massive area with what look like someone's laid tiling patterns there. You know, there's all these rocks, and they've got they're pretty regular, you know, rectangles, so on. And I put that down. And the first time I went there, I was measuring them. I used my shoes and I stood on them. I've got a picture somewhere. And one of them's there were some very regular ones there. You can see sort of at the top there, they're fairly regular. Down here, we've got some different ones fitting in. And they were about 1.1 times as length of my shoe. And I measured a whole lot of them. And yeah, it was pretty 1.1. And then I converted that to centimeters because I don't live in America. And it's a bit over 30, just over 30 centimeters. And I did the same with some of the other things. And the harmonic structure was clearly present, but I was using the wrong units. This is where imperial units win. So go on to the next one. This is someone told me when I was showing some of the stuff, they said Pythagoras says, "Are not rocks frozen music?" I'm taking their word for that he said that. But what we can see here, we can see that there's spacing. There's a 3 spacing, then a 2, then a 2. Between the red little lines here, I've done them perfectly regular. You can see there's a rock that's 3, then a 2, then a 2, then a 2, then a 3, then a 3. So that's our same proportions of 2 and 3.
So it's 3, 3 red marks here, 2 in here, 3.
That's right.
Well, this is 2 really, and 2, and then 3,
and 3 and 3,
and then 3.
Yeah. But you can see that the 3 that had 2 there, above it, there's 2 wider ones that make 3s again. And above the 2 that make 3 down here, there's some 2s again. So they coming in steps. They're coming in certain discrete sizes, which and I think it's because there's a wave structure there of those waves of 2 and 3 that's present. And when the rocks are splitting, it decides where it's going to split on the basis of that. It's got to split somewhere because as they dry out, rocks want to do that. So we've got those, and I've put musical notes there to show, that's a dotted note, and those are just non-dotted notes, and then some dotted notes. Okay. So I call this rock music.
Oh, that's good, Ray. Excellent. Rock music. Yeah. I love it.
Yeah.
Okay.
So the next one's just a repeat of that. It's just showing the left and the right are copies of the same thing, just showing how the rocks look and how the music notation on it is.
Rock music.
And you can see the 3s above. So you can see the 3s consistently through, and you can count the 2s off in some places as well.
You heard it here first, folks. Rock music.
Yeah. It's been around for ages. Now, there's a guy named Alexander Thom, and I think he was English. He was somewhere in the British Isles anyway. And he went around all, the stone circles like Stonehenge, and there's Avebury, and there's lots of other stone circles. We visited a couple when we were over there. You have to wander through someone's farm to have a look at them, and you can see these things. And they're all over the place there. But I've more recently discovered they're not just all over Britain. They were over in the north of Europe as well. And some of these things are being discovered in America now and other places, in Africa and all sorts of places. So this was a widespread practice of people thousands and thousands of years ago. And what Thom did is he measured the size of lots of these circles, and he made all his data available. So I downloaded his data and I did analysis on it with this quantization program, commensurality, what I call Kotoff method. Now, Thom said that he discovered a thing he calls a megalithic yard, and it's 2.72 feet. So you can see my one confirms there is something at 2.72 feet, but an even stronger one at 5.44 feet.
Which is 2 times.
Exactly 2 times that. And there's a bunch of others there as well. And they tend to have ratios, again, these same harmonic ratios. But the fun thing about it is that the larger ones, just under 22 feet and a little under 66 feet. 66 feet is 22 yards, which is a chain, right? One of the imperial units. And these other ones come to give you furlongs and other things. So all the old units that people used to use long ago are actually nature's units that it likes to do things in, by wave structures. And so now
that's a nice feather in the cap for the imperial measurement system, which isn't winning out today.
No, I have to confess, when I was a teenager, me and a friend wrote a letter to the paper when they were changing to the metric here for distances. Then we did it for money later on. Some old guy wrote a letter to the paper saying, no, these are nature's units. And we wrote a letter saying, do you think trees grow as 4x2s and things like that, and we made fun of him. And then later on, I discovered, actually, they are nature's units.
Isn't that great? I love that, Ray. It's,
so I have to apologize to that old guy.
I am so disappointed, let's say, in sort of the utilitarian view of the world that dominates today, that everything has to be sort of logical and rational and ready for computation, right? As if the only thing that matters is computing. And so that's just great to hear that those imperial measurements
so if we go
some
into the
correspondence with nature and are a deeper, really a more profound measurement system.
Now the next one. Okay, so these are the things I found in those rock formations. I found various other bits that had smaller ones, and I found things that were down to 1/2 inch and up to the fathom. These are the units that the imperial system has, and I've arranged them in the same way, dividing by 2 going across, dividing by 3 going down. And you can see, so all the things that have names in the imperial system in that range fit this pattern of division by 2 and 3. So people had effectively discovered these ratios of 2 and 3 in distance units long ago. The funny thing is, in printers, so we use lines and that in printers, right? In printing, when they do dots prints. That's one thing where the imperial system's measured to hang on. We have 300 or 600 and 1200 and other ones, dots per inch. And those ones tend to keep following the pattern of this with a ratio of 5 thrown in. So those
fascinating.
Now that links on up to those from the fathom. You link on up to furlongs and miles and all of those with ratios. And there is a ratio of 11 in there. When you go upwards from a fathom, which is 2 yards, times 11, you get to the chain, which is 22 yards. And so there is 11 in there. But when you're coming down, you're using 2s and 3s. And if you carry on a little while from that, you will get to Thom's megalithic yard, because if you divide a chain by 24, then you get Thom's megalithic yard. Now, I've got a sort of a little theory going that a fathom, the 72 inches, which is the 2 yards, is the standard height for man, though most of us are a little bit less than that. But the 2 megalithic yards is 11/12 of that. Take off a 12th, 6'6", and that's the standard height for a woman, but most of them are a little bit less than that. In fact, in most of these units, we find that in all of the stuff I found, the nature's ones and the ones that people have arranged rock circles are all about 1% less than the imperial units. So the imperial units somehow had 1% of inflation. But this thing about the height of men and women being different by 1/12 does seem to tie up with this. And I'll be interested to get the actual figures to see if that's the case. It seems to be, it's of that order anyway.
All right.
Now there's some more human ones. I think the next one's one of those. So this is a place in Greece called the Composite Goddess, there's lots of repeating structures, pillars, and there's rooms with tiles and things like that. And when you take all of those and look at them, the rooms, the sizes of them, and do Kodal's method again, I get these lengths in feet: 9.16, 11, 13, 16.6, 32.5, 43.3, 109, 130, 270, and 390 feet, which can be arranged again in proportions of 2s and 3s, just like that. And again,
right here. So portions of 2s and 3s. twos across and
and
threes
threes up. Yeah.
up.
And so again, the 65 feet is about 1% smaller than the modern chain, which is 66 feet. So again, it's all tying that together with Thom's ones and with these rocks I found on the beach.
Okay.
Oh, this is one. Now, we did the 160-minute before, but I think we did with the sun. But I missed doing this one. It's the Schumann resonance is the wave around the Earth, which is, people keep saying it's 7.83 times per second, but it's a little less than that on average. It ranges from about, it's around about 7.65, 7.6, 7.7, 7.8 oscillations per second. Now that's caused by an electromagnetic wave that goes around the Earth. Will get around 7.7 or something times per second.
Okay.
And so it's studied because it's quite important, and lightning and things happen on that cycle. So if you get a lightning bolt happen, say in America, it'll travel around the world and back again that many times per second. So the lightning bolts actually go about 8 times per second. But also at other locations around the world, and particularly, so I know you get a lot of lightning in the States because I've been there and I've seen fantastic displays of it, but they get even more in South America in the jungle there. And then if you go around the world in quarters, you get Africa, and you get the Indonesia, and you get the middle of the Pacific Ocean. And apart from the middle of the Pacific Ocean, those other ones are the ones that quarter waves are the waves of that around the world that show up very clearly. So, so that's showing this thing about the size of the Earth and the harmonics of the Earth showing up. But I took those, the Schumann resonances that are measured over extended periods by some of these scientific organizations. And what I've done here is I've correlated them at different lags to itself. So I've seen how similar does it become after various intervals to what it was before. And it turns out, you can see there, those asterisks I put at 160-minute intervals, and you can see quite clearly that the Schumann resonance is showing the 160-minute cycle as well as the nearly 8 cycles per second. So that was that's sort of a throwback to some of the other stuff. We're getting a few random things.
Kept cleaning up.
Yeah.
All right. So then just kind of wrapping up for today.
Yeah.
Right. We've been looking more in this bathtub area.
In that area. That's right. Yeah. Yeah.
And we see, again, these ratios of 2 and 3, particularly showing up in rocks, rock music, and in the structures of, these are, I guess, the distances between the stones.
No, the diameters of stone circles.
Diameters of stone circles.
The diameters will mostly be in tens of feet or hundreds of feet. So these ones are the ones that divide into it,
Okay.
All multiply.
And we see the same structure in actually the Imperial Unit system.
Yes.
And again, the relationships of 2s and 3s.
Yeah, so that one's an ancient site in Greece. And I've looked at a couple other ones, but it does seem that humans build things that did fit in with those natural units. I participated, I didn't actually go to Canada, but I participated in a Canadian conference where they were looking at buildings and how they're done. And I think there's a whole interesting subject around that. Last week I went to a conference in one of these lovely old churches that has these very high ceilings and fantastic shape, and it sounds beautiful in there when they're singing. And there's another cathedral that was built in Auckland, and they went to Arty Farty, on it. They built, they had the ceiling going up, and it did sort of like an M shape. I don't know if McDonald's had any part in this, but the result of that was when people sang in there, the waves bounced off the two parts, and certain frequencies got cancelled out. So if you played up a scale on the piano, it would actually fade in and fade out as you went up, according to how these waves, the ceiling shape was made all wrong. So a long time ago, people knew how to build these things correct. Like the whole Gothic thing and that, there's so in Europe, there's so many of these beautiful churches and designed around these proportions that people understood. In the modern time, you mentioned it before, that people have got away from that. And
I was in Chartres Cathedral, Chartres.
Yeah.
And the organ started playing, and I literally had the sensation that the whole cathedral was lifted off the ground and was flying through the air. It was surreal. Yeah. It was surreal. I mean, the acoustics were clearly so well designed.
Yeah. So all these Christian cathedrals are like that. I've been in some Buddhist ones in India, and the distances between the pillars, they've cut out places right from the solid rock on cliff faces and built things, and the spacings of the pillars and that, and they're all fit in with this as well. They used to do it, and they've got some groups today, they call it harmonic singing, and they do a type of singing. It's got quite a harsh sound. It's sort of sound that makes a heck of a lot of harmonics. And when different people do different notes on that, the harmonics of one, some of them will line up with the harmonics of the other. And when they have a group of people doing this, they can hear these waves are meeting up the top, and they can actually hear the sounds of some of those harmonics joining up. And it sounds like they're moving around up there like that. And they used to think it was angels joining in with them, you know, and doing that. And it's got that quality, you know, beautiful stuff, even though the sounds are quite harsh.
It would be interesting to look into Gregorian chant.
Yes, yeah. We're going to do Indian. We haven't done Indian music yet, have we?
No, we haven't.
We're going to do Indian music at some point.
Okay.
Yeah.
Well, since we have a little bit more time, we've gone. Today's session was pretty tight. I just wanted to go back and ask you again to refresh our memory about what exactly this is that we're looking at here on the left, the predicted pattern of prime ratios in cycles, because this seems important.
Yeah. So that's starting from that statement. That the harmonics theory, it's the universe consists of a standing wave,
right,
which develops harmonics. We can put in brackets there because the laws are nonlinear, and each of these does the same. And my contribution, people knew that waves made harmonics. My contribution is to say that each of these does the same. That hadn't been previously studied.
Okay. And so if we go back to the
that graph that's got the three things.
Where is it here?
Keep going. Not there yet.
Maybe is it?
That's the beginning of it. Yeah, that's the start of it, but go a bit further. Yeah. So that one there shows the whole pattern. That's going from 1 up to about 10 to the 50 odd. Yeah. Right. So maybe go back one again now so we can see the detail more. But in that, we can see that as we go along those, we go from 1 to 2, it's times 2. Times 2 to get to 4, then times 3 gets you to 12. You can keep doing times 2. The 8 and 16 are there, but they get fainting compared to the others. So the very strong harmonics, which I call the main line, they go times 2, times 2, times 3, times 2, times 2, times 3, times 2, times 5, times 2, and so on. Now, if we go back again to that numbers you had there, that's what that's showing.
So that was here. So that's just showing.
Yeah. So it's showing you all those
ratios of the peaks.
Yeah, that's right. The biggest peaks. And so all those 2s are there. And I've just arranged the 3s beside them and the 5s beside them to show how often each one occur. Each one occurs regularly, but the 2 much less frequently than the 2s occur. And so that's the whole predicted structure of the harmonics theory, is those ones there. And then then so that's what the harmonics theory says. The ratio should be between the strongest cycles in the universe at all scales. Yeah. And the middle part is showing how that's actually observed. We don't observe those very long ones. We only observe up to about 1 billion years. But that part there fits very well with what's there, which is why it lined up and worked out what the longest cycle is. And later on, when we get down to the atomic realm, we will see some of the higher primes come in a little bit there.
Okay, so is that where we're going next time, down into the atomic realm?
There's a lot of ways we could go. I think we go there, but let's take a little detour first. Maybe we get that one in as well. Cymatics. There was a man named Hans Jenny.
I remember that.
Yeah, before him there was who was he? Oh, I can't remember his name. There was another guy that did stuff before him, but Hans Jenny did this stuff with either fluids or powders where he vibrated them. And you get these fantastic patterns. And he did things where at one stage he had only 2 or 3 different frequencies. And this stuff made what looks like an insect, and it walks. It's only made with 3 frequencies, and it's doing that. And you think, wow, so when we see that, we can understand that in living creatures, they've got a lot more frequencies than 2 or 3. We can understand how we do more complicated things, but that's all it is, bunch of vibrations all cobbled together. So I did a little bit of experiments on cymatics just for the fun of it, and I accidentally found that that I may have discovered the meaning of charge and some other things, and so it shows what possible explanation is for particles and how they work with charges and other things. So we take a little detour through that before looking at things at the very smaller scale. There's both atomic particles. There's a structure in all the particles that we've found. There's a structure in the different isotopes of elements that we know. And that structure is quite fascinating, the how those ones all turn up. And then there's a link of that to the solar system. This is perhaps the juiciest part, that in the solar system, we had the outer planets and the inner planets. And you may remember there was a ratio of 7 in there. We went from 80 minutes to 160 minutes to 80 minutes, and then divided by 7. And it was a little under 12 minutes, and then we went 6 and 3 minutes, that those waves show up in there. That stuff, that 7 ratio between the outer planets and the inner planets, it turns out that the substances that those planets are made from show that 7 ratio as well. So the Sun, Jupiter, Saturn, Uranus, Neptune, are all mainly made of hydrogen and helium. And hydrogen comes in 2 forms, with mass 1 and deuterium mass 2 and helium 4. So we get the 1, 2, 4 there. The next thing the Sun will make, which was worked out by the Englishman, he should have got 2 Nobel Prizes. He didn't get any. He worked out the number 12. We'll get back to him. But then when you come to the Earth, what's the atmosphere mostly made of? Nitrogen, 14. What's the crust mostly made of? Silicon and oxygen. Silicon is 28, and oxygen, 28. And the core is made of iron, which is atomic mass 56. These atomic masses, not atomic numbers, because mass relates to frequency in quantum mechanics. So we've got this 14, 28, 56 going on as we go deeper into the Earth, whereas on those other ones and the Sun, you go 1, 2, 4 going in. And we got this, there's a 14 times difference in the outer planet solar system to the inner. And the same thing is true of what they're made of. And so when I've told this to people, oh, that's a coincidence, isn't it? I say, yeah, I've got more of them.
All right. Well, I look forward to looking at it next time. I want to go back for 1 second, though, just to the Schrodinger quote, because you mentioned something to me when we were talking earlier before we started recording about how this explains one of your cryptic comments in an earlier session, that you know, particles are no more real than economic cycles.
Yes. Yeah.
So why don't you say a little bit about that?
Schrodinger's sort of agreeing this. They're saying all material bodies are these oscillations in space, you know, appearances, and the particles themselves are not. They're not fundamental. And the trouble is with current physics and cosmology, they start from the smaller stuff, trying to work up to bigger and bigger things and work out how they work.
Right.
And there's some value in doing that. But the harmonics theory, when you test it, it shows quite clearly by those prime ratios that it's working downwards from the top, that the larger scale of the universe is the ultimate thing. And it's dividing up in these proportions. And they can't even get to making atoms properly from that principle of the things. Certainly not the molecules and bigger stuff. And I can get galaxies, stars, planets, moons, down on right cells, atoms, subatomic particles. All of that comes out if you start from the top. And the people that are interested in spiritual things and all of that, they much prefer it. And the people that are in alternative healing and things, they much prefer this top-down approach. That's the way they see it. As above, so below.
Yes.
We don't say as below, so above.
Absolutely.
Hmm.
The Platonists.
We should have a whole session on the spiritual aspect of cycles as well at some point.
Yes, absolutely. I'm reading a fascinating book right now called The Order of the Ages by a man named Robert Bolton.
Yeah.
That I think you'd find very interesting. He's got lots of 4s, 3s, 2s, and 1s in there.
Oh, okay. Yeah.
It's really fascinating. It's interesting about the just the idea that economic cycles are as real as particles, as atoms, right?
Yeah. We know the spacing of the stars fits the same economic cycle. So those waves are there. There's no doubt about it.
Yeah. And then what you said earlier too, that like the things that we perceive like particles, right, to some degree are related to the data that we kind of generate our experiments with. So, there's a footprint in the sand and it's our own, right? Some famous physicist said that. It may have been Schrodinger. We've seen a footprint in the sand and it turns out to be our own. Yeah. So that's the same with economic cycles, right?
Yes.
Or it's the same with particles. There's a footprint in the sand and it is our own.
Yeah.
All right. Well, thank you, Ray. Thanks again.
Thank you,
fascinating session. Look forward to speaking again in a couple of weeks.
Yeah. Radio. See you then.
All right. Bye.